Hey everyone, welcome to the first of what I hope is many PAMI Presents presentations. In this one, I'm going to be talking about selecting fans for grain conditioning and natural air drying, which is a very hot topic right now because of the less than ideal conditions that we have had for harvest this year. So in this video, I'm going to talk about why does airflow rate matter, understanding the role of static pressure and the fan type on airflow rate, and then I'll talk about 3 methods for measuring or estimating static pressure in your bin. So first of all, airflow rate really is the difference between aeration and natural air drying. Aeration is simply cooling or conditioning or evening out the temperature distribution within the bin, and the airflow rate required to accomplish that is relatively low, about 0.1 to 0.2 CFM or cubic feet per minute per bushel. And the physics behind this is pretty straightforward. If the air is cooler than the grain and you blow it through the grain is going to cool. Natural air drying, on the other hand, is actually removing moisture from the grain. And this requires a much higher airflow rate, about 1 to 2 CFM per bushel, so 10 times higher than the airflow rate required for aeration. And this is just because there needs to be sufficient energy within the bin to actually remove moisture from the grain. The physics behind natural air drying is a little bit more complicated. Basically, if the air has capacity to dry, then the grain is going to dry. And when air has capacity to dry is a topic for a completely different presentation. So the airflow rate that you get from a specific fan depends on what's called static pressure, or is really resistance to airflow. And the static pressure that the fan sees depends on 4 main things. Number 1 is the grain type. The grain type is going to dictate the size of the voids between the grain, and it's through these voids that the air is passing. So the smaller the seeds, the smaller the voids, and the greater the resistance to airflow, or the greater the static pressure. Number 2 is the depth of the grain. Obviously, the further or the greater the depth of the grain, the further the air has to pass, so the greater the resistance to airflow. Number 3 is a little bit counterintuitive, but really the airflow rate itself also affects static pressure, which then affects airflow rate. But basically, the faster the fan tries to push air through the grain, the greater the resistance to airflow. And this will become a little bit clearer later on when I talk about estimating static pressure with the available charts. The last thing you need to think about is the type of distribution system, or the ducting. So the geometry and the percentage perforations in the ducting are all going to affect the resistance to airflow, and I'll talk about that in a little bit as well. So the standard rule of thumb for fan sizing is 1 horsepower for every 1,000 bushels of grain. But that is not always applicable, or doesn't really account for the full picture, because nowhere on this list of things that affect static pressure does it say volume of grain, which is what bushels represents. Depth of grain certainly affects static pressure, but volume itself doesn't. So accounting for only volume might be misleading in a lot of cases. Really, you need to account for all 4 of these things when determining static pressure and fan size. So the reason static pressure is important is because the amount of air coming out of your fan depends on the static pressure that it's pushing against. So this is an example of the specifications for one manufacturer's fan. These are actually cheap fans. And this is one type of fan, a low-speed centrifugal fan. So how you read this chart is over here you have the models of the fan. And so this just represents chief fan, 22-inch diameter, -3, and this -3 is the horsepower of the fan. These numbers across here, 1 through 14, is the static pressure. So if you know you have a 5 horsepower fan and the static pressure it's pushing against is 6 inches, you go on this chart under 6 inches of static pressure, and the 5 horsepower fan tells me that that fan is going to be putting out 3,700 CFM, or cubic feet per minute, at that 6 inches of static pressure. So that's how you read these charts, knowing the fan size and the static pressure. So this is low-speed centrifugal fans, and this is a sample of information from high-speed centrifugal fan. So the main difference between low-speed and high-speed fans is the static pressure that they can operate at. So I generated a quick graph that shows the different types of fans and the airflow rates that you get from them at very static pressures. So all 4 of these lines represent a 5 horsepower fan, but the green line represents a high-speed centrifugal, The dashed blue line represents an axial fan, this purple line represents an inline centrifugal, and the red line represents a low-speed centrifugal fan. So the axial fans, this guy right here, actually can generate quite high airflow rates, like 10,000 and 12,000 CFM, even just with a 5 horsepower fan, but they are limited to much or fairly low static pressures. They are going to choke out at about 6 inches of water column. So they're suitable for low depth of grain or grain with really low resistance to airflow or having large kernels, like corn or peas. The high-speed centrifugal fans are much more suited for the higher static pressures, but their output or their airflow output is relatively low. But again, they are the only ones that can generally deal with the high static pressures. Okay, so static pressure is important. That's really what dictates the amount of airflow rate you get out of your fan. How do you measure it, or how do you determine it? Well, I'm going to talk about 3 different methods. The first 2 are actually direct measurements. The third one is an estimation method that is really better suited for sizing the fan before you actually purchase a fan. But method 1 and method 2 involve actually measuring the static pressure your fan is pushing against. Method 1 is simply using the pressure gauge that's already installed on your system. A lot of the newer bins with large fans will come with a static pressure gauge installed in the transition duct between the fan and the bin itself. So simply read the static pressure on the gauge. It'll likely be in inches of water column, which is the standard unit of measurement for static pressure. Just read that value and then go to the fan spec chart for your specific fan. So on this gauge right here, it looks like our static pressure is somewhere between 4 and 5 inches of water column. So I would go to my fan chart, and let's say I have a low-speed centrifugal tube fan on that bin, and it's a 5 horsepower fan. So I'm looking at this row right here, and if it's pushing against 5 inches of water column, I know I have about 4,500 CFM of air coming out of that fan. So now I divide that by the number of bushels in the bin, let's say it's about 5,000, and I get my number of CFM per bushel. So this would be slightly under 1 CFM per bushel coming out of that fan, which would be quite suitable for natural air drawing. If you don't already have a pressure gauge installed on the bin, you can actually make one and install one quite quickly. You're basically making a U-tube manometer to measure the static pressure in your bin. So to do this, you need to actually drill a hole in the transition duct between the fan and the bin, and the closer you drill the hole to the bin, the better. Basically, you're trying to be as far downstream from the fan itself to try to minimize the turbulent effect of the airflow right near the fan. So you're drilling a hole in the transition duct and connecting a flexible tube to that. So you can have a metal tubing connected to the duct, and you want to seal that off. You don't want air to be escaping around that connection point. So you are connecting this point to one end or one side of the U-tube manometer. And in the U-tube manometer, you just have water, and the other side of the U-tube is open to atmosphere. So the height of the U-tube itself will have to be sufficient to accommodate the static pressure that you're going to be seeing. So if you're expecting 10 inches of static pressure, then this needs to be at least 10 inches tall. Because once you turn the fan on, the water, or the difference in height between this side and this side, right here, that difference in height is going to be your static pressure in inches of water. So once that's connected, and once you read the difference in the water height, that is your static pressure, and that is the information you take again to your table. That's specific to your fan and fan type. So again, you're looking up here to see where the static pressure was in inches of water column, and then over here for your fan size, and then you're reading off the CFM from the chart, dividing by the number of bushels in the bin to estimate your CFM per bushel rating. The last method, like I mentioned, isn't a direct measurement of static pressure, but it is a way to estimate static pressure based on the grain depth and the grain type. And like I said, this method is really better suited for before the fact, when you are selecting the fan for that specific bin. So how this works is you need to use these charts that estimate the static pressure due to the grain type and depth alone first. So these charts were generated by the Ministry of Ag in Saskatchewan quite a few years ago. So they are somewhat limited to the grain depth that it actually goes up to. The highest grain depth that you can look at on these charts is up to 25 feet. So grain depth is on this bottom axis over here, and static pressure in inches is up this axis. Each of these charts has 3 lines on it, and each of these lines represent airflow rate. Because remember, static pressure depends on grain type, grain depth, and airflow rate, as well as the ducting. These charts account for 3 of those 4 factors that affect static pressure: the grain depth, the grain type, and the airflow rate. Because each of these charts represents a different grain type. If you look down here, this chart represents static pressure for coarse grains, like the cereals, and this chart represents static pressure for peas. And I have canola and flax on the next slide that we'll get to in a second. So to read these charts, you need to know your grain depth. You need to know your grain type, first of all. So let's say we're talking about wheat. So I'm going to look at this chart. And let's say I have a grain depth of 15 feet, and I'm targeting 1 CFM per bushel through that grain. So I come up this line right here that represents 15 feet until I get to the 1 CFM per bushel line. And so 15 feet crosses 1 CFM per bushel somewhere in here, so around 5.5 inches of static pressure. So that's for 15 feet of wheat. If I go over to this chart for peas, and I look at 15 feet for peas at 1 CFM per bushel, I am barely above 1 inch of static pressure. So peas, because they're a much larger or coarser grain, they don't generate as much resistance to airflow as wheat. Similarly, if we look at canola, so this is the chart for canola, and this is the chart for flax. If I'm looking at 15 feet of canola, and I go to this chart again for 1 CFM per bushel, I'm crossing somewhere up here, around 7.5 inches. So it's a higher static pressure than what was generated by the wheat for the same grain depth. For flax, if I look at 15 feet and I come up here to 1 CFM per bushel, which is this line, I'm actually off the charts. So the static pressure generated by flax is actually even higher than the static pressure generated by canola. Okay, so those charts take care of grain type, grain depth, and airflow rate. The last thing you have to account for is the static pressure due to the type of ducting. So to do this, you have to add the static pressure, or the average static pressure for the type of ducting that you have. And past research by PAMI indicates that full floor aeration generates very little static pressure. It's about 1 or maybe even less inches of water column. Partial floor aeration for flat bottoms obviously is around 1 to 2. And then the systems that were designed for hopper bottoms, so the rocket, the horizontal tube, or the inverted V, and other systems, will generate anywhere from 2 to 6 inches of water column. So, as an example, let's say we are working with wheat. We have a 15-foot grain depth above the ducting, right at the peak. We are targeting 1 CFM per bushel. We have an inverted V ducting system, and we're looking at storing about 3,000 bushels of grain in that bin. So we go to this chart. This is the one for wheat again. At 15 feet, I come up the chart to the 1 CFM per bushel line, and it looks like it's crossing, like I said, around that 5.5 inches of water column. So the static pressure due to the grain alone is 5.5 inches. The pressure due to the ducting, that inverted V system, is about 2 inches. So the total static pressure the fan is going to have to push against is approximately 7.5 inches of water column. So I'm going to go to the low speed centrifugal fan chart and look at 7.5 inches, which is somewhere between 7 and 8, but let's just work with 8 to be safe. If I'm operating at 8 inches of water column, I have to go all the way up to a 20 horsepower fan to get any kind of airflow. And that is going to give me 12,000 CFM for 3,000 bushels of grain, which really is overkill and doesn't make a lot of sense. So this is where switching fan types might actually be useful. So if I go to a high-speed centrifugal fan at 8 inches of water column, and knowing that I'm targeting 3,000 CFM so that I can get 1 CFM per bushel for my 3,000 bushels, now I'm looking at probably a 5 horsepower fan, maybe a 7 horsepower fan to do that same job. So fan type obviously is going to play a large role too when selecting your fan size. So, in summary, you need to know your target airflow rate. If you are only ever going to need to cool in that bin, then your fan size selection is going to be based on 0.1 CFM per bushel. But if you think you're going to need some drying capacity in there, then you need to size up and be able to accommodate 1 CFM per bushel. You can measure or estimate the static pressure due to the grain depth, grain type, and ducting system, and then refer to the manufacturer's fan specs to determine your airflow rate or the appropriate fan type and size for your specific application. So some upcoming videos to answer some more common questions that I've been getting. So just covering the basics of grain storage and management. I'm going to talk about some bin monitoring technologies. There's a lot of new technologies available and some that are just up and coming. When should I run my fans for natural air drying? Just the whole strategic fan operation side of things. And does adding heat actually increase the efficiency of natural air drying? Those are the topics for some upcoming videos. So thanks for watching, and we will see you again.